Hello, so this is lecture 23 in section 4, ensemble models, and this is module 3. So in module 1 and module 2, we have introduced you the backed decision trees and random forest. So in this third module, we will explain what is stacking type of ensemble models. And then next, in the module 4, we will talk about boosting type of ensemble models. Let's get started.
Okay, so before I talk about boosting, I want to talk about stacking. So to talk about stacking, there's a really classic competition which got an ensemble into people's eyes is Netflix prize. So I think you maybe all know what is Netflix competition, which is this user movie reading competition. So there's a lot of training data. It's about 100 million data. And then you're trying to predict for a new user, what's up there are their ratings. And this is a 1 million prize for 10%. So whoever achieved 10% improvement over the Netflix baseline, you're going to get a 1 million prize. So people in the leaderboard just try really, really hard. And who is the first, right? So it's not who is the best. Here is who's the first to reach that 10% improvement. It's a very funny, actually, funny story. So this group called, it's actually a matrix decomposition based idea. I think it's from Intel. It's called Balker's Pragmatic Chaos. And then the second team is ensemble based. And the first team and second team actually got exactly the similar performance. But the first team is 20 minutes earlier. So the first team got a 1 million prize. But this still tells you how powerful is the ensemble models. In fact, the ensemble models here are just diverse of kind of predictors. And it's not complicated at all. It's a complicated model, but it's very heuristic driven. The first group, it actually has a lot of, it's this specific task grounded approach. It's a matrix decomposition based approach. You should check out the first method, but second method is like a pipeline. And if you check out the recent Kaggle competitions, and in fact, you don't even need to understand the data much. You just run an ensemble of a lot of algorithms. And normally, and as long as you don't do stupid mistakes in data processing, that type of data processing mistakes happen a lot. And you formulate correctly to using each of the base classifiers, you have a reasonable blender to put them together. It always gives you really solid, good results. All right, so what is stacking? So we told you about ensemble, about random forest and bagging, and owing to blending approach we told you is majority voting or the mean, right? 1/b, summation of each fi. But think about why do you need to limit yourself into those heuristic-driven max function and the mean function, right? If you think about what we use in the majority voting is max function. And what I use in the 1/b is the mean function. You really don't need to limit yourself to that type of fixed function. Yeah, mean or max or some other type, uniform summation, or how about just train a second level blender, second level classifier, or second level additive summation with the weights. And we try to use the second level to get the best weights to do the combination of each base classifiers. And this is normally called a meta learner, or we can see that they're blenders. And then to perform the final prediction. So this, everything here, so if you treat a meta learner, so whatever meta learner, it all follows this, you can call them a stacking model. Because it's stacking a second meta level classifier on top of the base classifiers. So question about this? It's extremely easy. The prediction from different F1, F2 onto Fi, F1, I should use B here, like Fb, and then you have a different level. Let's see the G function. In the end, you're learning a new function G to combine F1 to Fb. Sure.
Is this G kind of a linear function only, or it can be any?
Can be a lot. There are many different kinds. Yeah. The most intuitive is a linear function, right? And you really just learn the weights of each, the weights on top of F1, on the weights on top of F2, the weights on top of Fb, right? But you're really not limited to just linear function. It's just another classifier you can think about.
Because before we were just taking the mean or the max.
Exactly. So what we did in the back and it's either mean or either max. They're just fully heuristic driven, right? So maybe some base classifier is more important than some other. You don't want to just treat them the same, right? So this gives you another level of flexibility to consider the different base classifier in through a different combination. All right, so there are many kinds. Then in the end, for your base classifier, you need to think about accuracy and this diversity, right? It needs to be not too strong bias, not too similar to each other. And how do you create F1 onto Fb, right? You sample the training data, or you sample the feature, or you use different models. You just use different method. SVM, k-nearest neighbor, whatever, things seem making sense. They can all be a candidate in this as a base learning. And then how do you put them together? So what I said, it's a supervised way, right? But you can also use unsupervised way. Like we said, majority voting or weighted mean, there's even k-mean space, which we're going to cover later. So in the next about unsupervised method. How do you train it? So you normally need to split your training data now into two sets. The first subset of training data is used to train different base classifiers. So F1, F2, onto Fb. And then on the second training subset, some people call that validation data, or So you actually on top of that subset, you're training the G. So this is the output from F1. You're using all the output from F1 to Fb as features. And then you're training a second level G function using the F1, F2 onto Fb. And so in the end, you are using a different, a left out to train the G function versus the Y. And there's a loss function here. Again, the same procedure, right? Loss function Y versus the G, and then you can use many different strategies to train the G. Okay, but pretty critical. There should be differences among subset 1 and subset 2. The one used to train the base learner and the one used to train the meta learner. All right, okay, so questions about this? Sure.
Generally, I mean, let's say all these functions are only decision trees, and in another case there are like decision tree, SVM, KNN, and like different ones. So does the variance matter? I mean, in the first case there will be more variances compared to the later case or something.
Yeah, so very good question. So the question is, if F1 onto Fb, they are bootstrapped different decision trees. And this is the first case. The second case is I don't change my training data, I change my training algorithm. So I train SVM, k-nearest neighbor, decision trees, or maybe logistic regression we learned, 9 days. These are also variations, right? And then you train a different level of G function. So which one is more preferred in this case? So I think, in fact, for the stacking kind of model, I think the changing the algorithm is more preferred because there's a much better strategy when you F1 to FB they are all decision trees. There's a much better strategy. You don't need to do so they're much smarter stacking. If F1 or F1 to FB are all decision trees, the much smarter stacking approach is actually called boosting. It's exactly after the stacking I want to talk about it. It's next.
Great. So this is the end of this module. See you in next module.